Okay, I don't know. Maybe this will work, maybe this won't work. But let's okay, so we are trying to derive the amount of kinetic energy. Hold on. The kinetic energy of a non-rotating mass traveling at speed v is okay. So all we know is that this thing is this mass m is moving at a velocity v, and we could just call something the kinetic energy and set it equal to this random expression. But we need to remember the definition of kinetic energy. Kinetic energy has units of work, which is joules, right? Yeah. So joules. So if an object with mass m is moving, going with velocity v, then we want to know we want to know, I guess, how much work had to be done on it to get it to move with velocity v. Okay. Okay, what I have is that kinetic energy is defined as an amount of work. And basically, the question that it seems to answer is I see some mass moving at a velocity v, and I basically want to know how much work needed to be done on that object in order to make it move with that velocity. And now we want to derive how to figure out the answer to that question. You know what? I always have to humble myself because like I always feel so dumb, but it's like this stuff is actually really cool. So, right, the definition of work in one dimension, if a net force F acts on an object and moves it along the x-axis from 0 to xf, okay, so W is equal to the integral from 0 to xf of the force with respect to the distance. So Okay, but a force, but force. So the force is the mass times the acceleration. So we could rewrite work is equal to the integral 0 to xf of the mass times the acceleration with respect to the change in position. Okay. All right. So now we can go back to actually thinking about the golf ball. And why I so why are I get why conservation of momentum makes sense because no energy is being lost, but what is the justification of conservation of kinetic energy? I guess it's kind of the same thing, right? Okay, in book one, in the Principia, Newton begins by defining two key concepts: quantity of motion inherent force. Newton speaks of a body's tendency to maintain its state of motion as an inherent force. But that is something different from an external push or impressed force. The inherent force is simply what keeps something moving uniformly unless something else acts on it. It is in the second law that encapsulates F equals m. Precisely says the alteration of motion, the change in quantity of motion. So quantity of motion is defined as the momentum. So dmv with respect to what though? The change in quantity of motion is proportional to the motive force impressed. Okay, and then here he defines the change in momentum with respect to time is a force. And that's what he calls force, is the change in momentum. You know, reading this stuff, it's kind of amazing that the universe does have such simple laws, and you know, it's like we could have guessed anything, and we guessed just the mass times the velocity. It's as simple as that, and it works pretty good. Okay, okay. Imagine a small object in a horizontal track. If you apply a force, remember, a force is a change in momentum. So then, Okay. Mm-hmm. That checks out. Now, all right, I just had to fix the mounting of this thing, but let's get back to work here. Uh, How do you derive it again? So we applied 10 newtons of force for but the force is constant. So let's just see. Let's work through finding the work, final velocity, and position if we are applying 10 newtons to a 1 kg mass for 10 seconds. Let's figure this thing out, bruh. We're going to get to golf in a minute, but first I got to catch up. Catch up in the past 400 years of physics, Just a little review. Okay, so we got to that. And then we got this. And we got that. Okay, cool. Now we can finally go back to momentum transfer. I'm going to clean up a little bit. Let me get some water. So let's right. So we're just figuring out what the um oh wait, we didn't even try find multivar. All right, so now we want to. Okay, wait. So we should have. Oh wait. Oh yeah, we ran out of internet. I forgot. That okay. We had to take a little detour, but now we're good. So we just have to add this package for doing a Grobner basis, which is basically solving multivariable equations. That's all good. So we're gonna solve for and I want to know what form they're gonna give me these solutions in because that'll be interesting. It's got to compile a whole computer algebra system. That's fine. I'm chill with that, bruh. I'm chill with that. Um, I don't know how 4 people are watching this. This is boring as hell, bro. So, anyways, what we need to do is hopefully this will give us the set of solutions in a not crazy way for V1 and V2. And then this will give us not only the velocity, this will also tell us the velocity of the club after it gets hit. All right. So wait, was that the solution? Oh, we didn't even do using. Bro, what the hell is this? This is how you know nobody uses this stuff, man. Like, what is this? Who the hell wrote this? Anyways, it doesn't matter to me. As long as it works. Cannot, can, bro, what? How are you supposed to use this? Is there any docs for this at all? Eeks of type vector and then vars of type vector of num. So what did it try to convert? Okay, so this just doesn't work, right? If we were to look here. So this is the, yeah, okay. So this, and this just doesn't work, I guess. So is that known that this just doesn't work? Oh wait, let's try this. Symbolic solve. Wow. Oh my god. What a joke, dude. It's like how is this a computer algebra system? That's terrible. You can't even solve this. So then what does that mean? That means that we have to like just come up with the expression ourselves. Okay, so let's just do this. So you get all the way down here and you find, right, yeah, you do this, that's all good. You rewrite, and then you get, yeah, so a v1 squared plus b v1 is equal plus c is equal to 0, where a equals m1 plus m2, b is equal to minus 2m1 u1, and c is equal to minus m2 minus m1 u1 squared. Okay, great. So, all right, so we can ditch this, but what we are going to do is we're going to say a is equal to m1 plus m2. This is just going to be an actual number. B is equal to, so the these equations represent conservation of momentum and kinetic energy of the system. This allows us to determine what the velocities of the club and ball are after the collision, given their initial velocities and masses. Great. So since symbolics is a joke, we algebraic simplification of the equations gives us the following expression for V1. A V1 squared plus B V1 plus C is equal to 0. A is equal to this. This is equal to minus 2U1, and this is equal to C is equal to minus M2 minus M1 times U1 squared. Okay, so these should all be real numbers. Okay, so then we should get that V1. Let's see, is this going to work? Symbolic solve. If it's a scalar equation, it probably can solve it, right? What if it couldn't even solve scalar equations? Okay, great. So that's good. Oh, and it does this rational approximation. I don't even want that. So wait, let's just do float. Wait, first off, I should not have made it v1 real. We should have not done that because that was not good. Okay, okay, so let's do this. Wait, is it symbolic? It's literally not a symbolic number. Dude, their type system is just stupid. I don't care. I do care though, but I shouldn't care because it's just so bad. Um I don't care. I care so much. All right, let's just do v1 is equal to minus b plus, so wait, v1 plus square root of b squared minus 4ac over 2a. Okay, then we get this one. So wait, what do these two solutions represent? And so then, now that we have that, what do we do to calculate? So we get v1. So we should be able to plug into either of the equations here. So wait, let's just say const moment equals this. Cons kinetic equals this. Wait, what happened? Oh, oops. Cons moment, cons kinetic. Okay, and what we want to do is we want to do substitute cons kinetic v1 goes to v plus. Okay, and then we get this thing, and then we can do a solve for symbolic. Oh, good. Well, that's nice. Okay, at least it's exported, so they're like, all right, you should be allowed to use this. Symbolic solve substitute v2. Okay, there we go. So then we get v2 plus, oops. So now one of these solutions should be nonsense, right? How is this taking so long? Please do not run through the freaking Grosvenor code path. I'm sure it will, but it just really shouldn't. I'm like, what is it doing, dude? It's solving a quadratic equation. It's not rocket science. How is anyone expected to use this thing, man? Is it known that the freaking symbolic solving is just completely broken? Cash miss, cash miss. Oh, okay. So we need to, okay. So we need to find the solution. Okay, wait. So okay, that's fine. I mean, we can always just work around it by doing it like this. So we have this. We have U1. What? Neither of them are. Okay, but. Okay, maybe it's like flipped around or something. Please don't crash. I feel like it's going to crash. God. Okay, so this. Great. So this stalls Julia completely. So we can't do this either. So we're just gonna. I don't even know how that happens. How does that even happen? All right, let's just let it run for a bit, but I guarantee you that it's not gonna stop. Okay, yeah, but that's the thing is the symbolic solves are garbage anyway, so it's okay. But the problem is... Oh, God. Is there another solve? What a joke. Oh, God. Okay. First off, this isn't even a real expression. S log. If you did S log, it's like, this isn't even a real... I don't even know how this got in there. I wonder if we can just manually call solve univar. But I feel like this is still going to shell out to... Like, if you have different solves, why don't we have a method picker? Come on. So, whatever. So let's just... Because what if I have both? Don't I have Nemo in here too? Yeah, let's read this. And there's no way to pick? Surely there's a way to pick. Okay, wait. So let's just try solve univar. Symbolics.solve univar. So this is going to be v2 expr. Solve univar v2 expr v2. Let's see this. How is this going to do? What? I mean, my guess is that this project is pretty much atrophied and it's... No one's really working on it. You know, it sucks when there's... Not bad. All right, so let's just say... I mean, it's like really slow. Oh goodness. It's like really slow, man. This thing takes forever. I'm almost tempted to benchmark it because I want to know how many allocations it makes. Oh my god, dude. That's crazy. Okay, wait, how do you get the so now I just want to get the Okay, wait, hold on. Wait, but why don't we just do this? Why don't we just manually find the expression that okay, so then V2 let's just leave that. V2 real is equal to so wait, but why did that's the really bad part. Is like why so we need to figure that out. Oh lol. Okay, wait. Yeah, so let's just do we can just do uh V1 real equals quadratic solve ABC. Yeah, okay, good. So we get this. Oh, never defined it. Okay, great. Okay, so now find first x to x. Does this work? Not approx. This is V1 real, right? Oh God. Okay, so now we have not is a prox x u1. Does that work? Okay, so then we get v1 real of this. Okay, now v1 val is this. So then we can take, so we don't want to substitute. We want that v2 expert is, we got to go all the way back up here. It's equal to 2 times 2m1 divided by times u, whoa. Okay, and is that just going to give me a real number? But see, that's not what I want. I want the actual, I want the other one. I want m1 over m2 times u1 minus v1 val. Okay, it's the same, but that, okay. So more algebra and we get the golf ball velocity. Finally. Okay, this is just a joke. I mean, yeah. No one cares, but it's like it's going to take, at this rate, it's going to take them, 5 years before they can solve a polynomial. Oh, that and with an experience that doesn't suck. And that's okay. All right. So we could completely forgo. All right. So ball. Wait. Let's do .get ignore star.csv. Okay. Okay. So and what was v1 val? Okay, great. So now we can just clean up this. Actually, should we try this one more time? Oh, no, but this one errors, I think. Right? Yeah. That's stupid. So the idea then is that if we get to, we want this, but we want like let's say we have some parameter has collided equals 0. And then this does not work. But if we had this, then we go has collided goes to 1. So But I wonder if, what if we just made that a state variable? All right, what if we tried that? Why is this yelling at me? Is it because of this? Oh. All right. Well, okay, wait. Let's try it with this one. But the thing is that wants to modify both parameters and unknowns. This is currently not allowed in one individual callback. Okay, wait, but if this happens, then we can just do this, right? And then we can run this. Okay, but if we solve this, do I get to... Like, does it log it automatically? I don't... Let me, let's go back to that documentation on events. So here's the language. Oh shit, that's not what I want. Okay, but if we do sol dot well, okay, that's why I think we should just wait. Discrete safe subsystem dens k residual alg prob sense. Let's just look up events mtk Julia. Parameter. So these are parameters. Okay, so you have this constant velocity. And okay, that's cool. Yeah, this is fine. Then you do it. I don't know what this is about. Cos 100 theta minus pi over 2 is equal to 0. One of two ways. Edge sign detection or right root finding. For exposition, well, okay, that's fine. So this is the other way to do it. And then this is how you simulate, wait, QA, QB. Why do you do both? Sol.ps. Yeah. Funny. Okay. Just give me the whole thing. Nice. Okay. So how do we actually, oh, there we go. What is CNT? Oh, it modifies the count to go up. Okay, but it doesn't actually, so what we want then is to just do it like this. We're just going to make it a state variable. Okay, so this should work too, right? Um, okay, so you definitely need to look into add coupling has collided flag in system. How do we log it and plot it? Because like it's not a variable that's governed. Oh wait, you know what? Maybe wait, let's go to the actual docs. We just need to be patient. So the docs of the language. Let's do this again. Because I think there's oh, at description. That's nice. So let's put this in at description begin end, and then the formatter of course doesn't work on that, so that's okay. Or actually no, wait, that's kind of, well, okay, that's just a weird thing. Constants, defaults, equations, extend. Ooh, icon. Parameters, structural parameters, non-sim variables. Equations for the list of equations. Wait, so what is constants? That's pretty cool. Wait, let's just see if this works. Okay, so let's go back to this bad boy. Wait, what? Why did that happen? Oh, wait, what? Did I just misspell it? Description. Okay. Invalid description. Oh, did we just give it a string like this? Bro, what? It's like they really have not tried anything. Oh my god. Invalid. So now I want to do first off, I want to look at the data frame to make sure that we should still have goal 0 plus. Oh, and of course, okay. So it doesn't even. Okay, so it stopped. So wait, hold on. We need to test. So then if we do this, wait. Right, exactly. So that fails. So that's hilarious. Okay, that's fine. So then, wait, but what if we just do 2 of them then? Or you don't do a comma, you just do it like this? Okay, does this work? Okay, and now if we look at golf, we will see that we have zeros on the theta. That's great. That's very good. So we fixed that. But now what we want to do is we want to do sol dot. So if we do like sol plot sol indexes, which I mean it's just terrible design, but that's okay. Sys1 dot theta. So let's just do this, and then we will see. Great, we get that. That's fantastic. But now what we want is has collided. Right. Collection must contain exactly one element. Sys1 dot has collided. Indexing with parameters. Okay, get p. I mean, wow. This is. I mean, wow, dude. This is really bad. Okay, and then can we index with this now? What if we just do, if we do symbol of theta, this doesn't work, right? Oh, wait. Oh, so this does work. Okay. So you can index by a symbol and you can index by that. So let's try to index by has collided. Indexing with parameters get p a. So what about, okay, so modeling toolkit dot get p Sol has collided. Um, this is ridiculous, dude. So this doesn't even do what I want. So how are we going to do this? We need to do this in a different way. We need to, when we pass it to ODE problem or something, we need to do some weird external. I mean, I don't care about performance, so that actually is fine. So discrete events is what is a discrete event? I don't even know what that means. Oh, so that's kind of nice. No, it's involved in a differential equation, right? First off, this syntax is totally arcane to anyone that doesn't know what it is, so that's hilarious, but that's fine. Discrete events. What does this mean? Oh wait. Sol indexes equals has collided. They should just rewrite this thing. That would be the best thing to do. Is just like start with a blank sheet of paper and just be like, all right, if we're gonna rebuild this thing, what do we need to do? Clearly, you need to start symbolic. The more that, yeah, whatever. I don't care. That's pretty cool. What we should do though is run this example. I wish they have clicked a copy, but it's like I'm gonna have to. What's up, bro? So right now we're trying to. Honestly, this is all in the weeds. But okay, let's just do heater. All right, I gotta test something. All right, so we do this. I'm sure this in. Okay, so we have this. But then where do you put that? Where is that? Okay, so let's put this here, even though I don't know what that does. Okay. All right, here we go. The system. Okay, so let's see if this works. So this is less linear algebra and this is more differential equations, which is like systems that change in time continuously. And what we're trying to do is model a golf swing. I'm pretty sure this is deprecated. I guess it's not. I actually like their effects interface now that I'm getting more used to it. It's actually pretty cool. It's at least it's flexible, you know. Is this sample of a? Did you swing it yourself in? So okay. So the model that I have right now is actually really dumb. It's basically imagine that you have like a pivot point and you have the club and you just like let the club go and then you just let gravity do all the work. So that's the model that we have right now, and I'm trying to improve it. Um. Um. Okay, so here's the problem. So we need to figure out okay, so it was a parameter. So furnace on of T was a parameter. Oh, but you know what? If you make it of T, wait, let's see if we can try this in golf. Has collided of T equals false, and you have to assert that it's a bool. Does this work? Okay, wait. Let's go back to here before I get ahead of myself. So if I do sol of, if I do data frame of sol, it only includes dependent variables. So that's not ideal. But if we did sol of heater on, does this work? Or furnace on? furnace on. Damn. Because the thing is, I just feel like they don't recognize that it's super useful. Or wait. It just seems super useful if that to be able to. Okay, so we need to take a step back and we need to reread. Saving discrete values. What is a discrete? Time-dependent parameters which are updated in callbacks are termed discrete variables. Modeling toolkit enables automatically saving the time series of these discrete and indexing the solution object to. Oh, that's perfect. Consider the following example: parameter c of t. Okay. At time 1, I think this means at time 1 when t is equal to 1, but I don't know if that's actually true. I don't know what this means. Then c goes to c plus 1, and you can index this. So wait, so if we, but in here we have it at discrete events block. But the thing is, it is kind of a continuous event in a way. Because this is a continuous event. But maybe I can just do. Okay. Because from this, we want to know. I mean, more so just for correctness and doing things the right way, I want to have the effect not be a discrete. But you know what? If I have the discrete event and the continuous event, then I think it's okay. And discrete events get logged, right? So if we go back down to where's our section? Saving discrete values. If we did this, but the thing is, all right, let's read discrete events. Let's read this. Because I don't know why it says 1.0. That's the weirdest thing to me. Effect 1 and effect 2 are either a vector. I don't even know why that limitation exists, but that's okay. Yeah, that's pretty cool. This is actually really cool. I like that. So how did this work? Injection when T is equal to, but does it apply exactly at T inject? Or did they have to do, they had to manually specify that this was a T stop. But the thing is, this is why you want a continuous effect for when theta is equal to 0, because you don't know when T is, you don't know when that's going to be. So that's where that comes into play. Okay. Oh, this is the format that, see, this is, they should just get rid of this, right? Like, so that's why they had the 1.0. Yeah, they should just get rid of this. This is too much sugar, and someone that doesn't know the this special for, so they should just delete this. This is all just bad, but that's fine. What about the periodic? How do we do periodic? Okay. One advantage is that one does not also need to specify a T stop. Oh, okay. Well, then I get it, but they should also just use their symbolic machinery to find out when T is, if it's possible, and if it's not, then they should throw a warning or something. A periodic event is triggered at fixed intervals. Wait, so then in this case, it should be every 1 second. Okay, so this is a period, so they should say that this is a periodic discrete event. Okay, but that's cool. I mean, because this is what we want. Because then we can make we can plot, because, all right, wait, let's just do this. This is going to be this discrete event. All right, we're going to delete this, but what I want to do is I just want to plot sol indexes, and then let's just get rid of this crap. See, I don't understand that. So we can do sol of C, okay? And then we can make the pairs, but we can't do plot sol indexes equals C. So this is broken and this is a bug. Because if a discrete, it basically says that their plot recipe does not support what they call discrete variables. So that's a bug. This is definitely a bug. I don't care though. So we have to do this plot sol.t, sol.c. And for some reason it's not even loading. Wait, why isn't this? Wait, what? Oh my god. Wait, what? Oh my god. This doesn't even do the sensible thing, bro. Oh my god. That's insane. Okay, so that's pretty cool. So we can find Sol. Let's say, okay, wait. Sol of 3 gives me, dude. Okay, this just gives me literally a vector of U. Yeah, dude. The whole they need to rewrite it now that they have this symbolic thing. They need to rewrite all the old stuff because oh my gosh, it's just like what the hell, dude. You don't want a vector of float there. You want some you want some symbolic thing that is context aware of your situation because here like this should represent like the system at t equals 3. Anyways, so okay, so this thing is a total joke because it's not going to work for our thing. Time-dependent parameters which are updating callbacks are termed discrete variables. Modeling toolkit. Wait. Actually, you know what? Hold on. Let's go back to golf because I'm not actually positive that I'm pretty sure that they're just omitting a really important piece of information. And what we want to do is we want to change this to true, actually. Okay, so now what I want to do is sol. So wait, how did they? Let's just make sure we did it the right way. So sol of C, but that's because they did this thing. But if we just do sol of sys one dot has collided. Let's go. Actually, that's great. So that's great. The only thing that's busted is that it's super hard. Okay, so we need to. Okay, so this is really cool. So this gives us. This doesn't really make sense, but it does show that we can index has collided. But it doesn't make any sense because it's not like you can plot this. From what I can tell. So that's okay. But you can okay, but so I was right in that they say saving discrete values and they only use a discrete event, but they should give another example with a continuous event and be like, okay, you can index this. But actually, you know what? They probably have that. They probably have that somewhere in this. No one's gonna read this. I don't know why they. I mean, maybe someone, but this is too much stuff. In the former, equations that evaluate to 0 will represent conditions that should be detected by the integrator. For example, to force stepping to times of discontinuities. The latter allow modeling of events that have an effect on the state, where the first entry in the pair is a vector of equations describing event conditions. And the second vector of equations specifies the effect on the state. Each effect equation must be of the form Okay, so this is the first thing where they say, look, I want you to step at when the velocity is 0, I want you to step because there's something special happens there. An example where a bouncing ball is simulating using callbacks in which an effect. We can model this same system in Modeling Toolkit by reversing the velocity when it hits the thing. That's so cool. I actually love this though. I mean, it's like terrible, but it's still really cool. Okay, wait, let's read this because this looks like the good thing. Because this is the most general where I can just like log everything, even if it's inefficient. Oh, yeah. Okay. Jesus. I don't really understand this, but I can see why it's the most generic. Okay, so we really kind of have a handle on this. So the main thing is that there's just not a plot sol indexes has collided. This is the main thing that's broken, right? Okay. So now we're going to build another model that so one thing that's important is one thing that we want to do maybe is we like sort of did this, so we discrete variables is what they call this. Okay. I don't even know if I want to fix the moment of inertia thing. I think point mass is pretty good. So what we want to do, though, that's important is figure out how to um, end the simulation with an event. Basically, we want to stop simulating at that point. Oh, this is what I want. Yeah. Wait, but is this going to be a discrete system? Wait, observed sys? What? Ooh, this looks like what I want. Wait, does this work? This looks pretty good. I saw that this is in the docs. Yes, so this is okay, so this is the issue. This is um so plotting is related to this issue. Yes, this is exactly the error that I'm seeing. And of course, it's like 6 months old and nobody gives a shit because everyone's busy. I get it. But it's like, let's just see discrete event. We're going to copy this. Let's just do it below. So we're going to do bing, 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 bing. So does this work though? Oh, what? So wait, oh, you can plot it with something else, but you can't plot it on its own. Okay. That's pretty sweet. Okay, so wait, I think we're actually good. Then we should be able to just plot so wait. Okay. We can do plot, stall, indexes, and then what are we supposed to do? We're supposed to do sys.c. So sys, wait, is it a tuple? No, it's an array. Who knows what happens if you change anything? Sys dot yeah, theta, and then sys dot has collide. Variable theta does not. Oh wait, one. Okay, why didn't that work? I think it only works if collection must contain only one. Okay, wait, let me just. God, I feel like I'm so close to. All right, so this one worked, right? This one gave me something beautiful. Oh wait, but you know what? It's because this is golf or sol golf. We need to do this. That's probably why. It's because I was being careless. Let's go. Okay, that's awesome. Okay, so we did it. That is so cool, man. So you just can't plot it on its own, but you can plot it. Oh my goodness. All right, so that took a little bit of nastiness, but that is really great. That is so cool. So because of you need to plot it with something else for some reason. And this is like the good old days, back when I really liked Modeling Toolkit. Now I just have disdain for it because of how many weird historical accidents there are. Just like crazy tech debt, just like crazy, crazy tech debt. But so this is good. This is good. We can see here that it shifts from 0 to 1 at time when theta is equal to 0 on the first theta, and it just stays like that. Presumably, we can also do something smarter than this, but let's just get to the second system. So we're going to make our ball system. So this is going to be, let's just copy this whole thing, and we'll just delete everything. Okay. All right. So let's just go like this. Okay. This model, so first off, it's going to be called the simple ball model. Wait, actually, but I do want to figure out, we want to add an effect that basically, instead of doing this, we want to completely terminate the simulation. So I mean, there's sort of two paths we can go down. We can like do the hit and keep simulating the swing of this, but it's kind of a waste to do that. But what I do actually want to know is, okay, so what we want to do, what I want to do is, okay, so I did find a solution there, so that's good. Figure out how to end this, that's good. But what we want to do is we now want to use, add an effect that on the first collision, we reduce the velocity of the club by the correct amount. So what that means effectively is we're going to need to do all of this math. Do we actually need these equations? I'm pretty sure that we do not need those equations because we just need these. So we really just need to do two quadratic solves. Or no, we need to do one quadratic solve, then we need to run this code. So this is really the code that we need to run inside of the simulation. And I really do want to do this compositionally in a way that like we have these two models and we have a higher level model that contains the effects that on the on the first collision, because connecting them is going to make way more sense than throwing this all into one model. But represents simple given an initial velocity and angle, we compute how we solve for the trajectory. So this is going to be in terms of x of t and y of t. Okay, and we can also include a small, so a roll component. Yeah, so okay, so we could do, I don't know if the ball necessarily bounces, so maybe we could do a bouncing ball model. Because unfortunately, fortunately, I mean, it makes sense, but the way that, you measure the length of your drive is not based on where it hits the first time, but for our sake, we will just end the simulation when I will attempt to end the simulation when on the first instance, or basically when t is greater than 0 and y of t is equal to 0. This will, the thing is that there isn't really, I'm trying to think, but there isn't really much in the way of differential equations in this case. So, okay, so I think the most important thing that we need to do, we can just run 2 simulations for now. So the simple ball model is what we're doing now. And we're going to figure out, and then I'll end the stream because I need to go on a run before class. But we'll spend 20 more minutes on this or something. Okay, I'll be right back. Okay, so so the parameters are going to be ball mass is equal to 0.045. Let's just do kg. We don't need to describe all. So let's just make so then the radius doesn't matter either, but what we do care about is the angle, the initial angle is equal to, let's do pi over 4. Okay, so this will be, so then we're going to have x of t is equal to 0 and y of t is equal to 0. So this is going to be the horizontal position of the ball and position of the ball meters. Okay, cool. So then we're going to have their equation. And so yes, so we're going to have, so the velocity, well, okay, so here's the thing. The kinetic energy of the ball is going to remain constant throughout the simulation, right? But actually, that's not true because there is a force acting on it to change its kinetic energy, as in the total velocity. Yeah, for instance, if I threw a ball straight up, there is a point at which the velocity is 0, and thus there is no kinetic energy. The ball has no kinetic energy. So So actually, so these are the positions, but what we're going to have is we're going to have like D times cos, because the initial angle is going to be with, and this needs to be radians from horizontal. Okay. So then D of x is going to be cos, because it's going to be that divided by that. And then this is actually true, and we need to add in back gravity. So we need gravity as a parameter. And then this is based on time, right? The change in y and here we need, so here we're going to have a parameter for initial velocity, and there we're just going to leave this like this, except this maybe we can interpolate into that. This is an expert, this is just the val, so we can actually just wait, v1 v2 val, let's do that. v2 val. So okay, so that's cool. So now what we want to do is, here I would love to stop when the, so that's one way of doing it, but that's a really dumb way of doing it, because we need to run the simulation until, so maybe maybe if we did this and we just made it a steady state problem, that would actually be fine. But I don't know if I want to do it that way. I want to terminate the, okay, so let's see. Does this system work? Okay, so this is going to be simple ball model. And this is going to be sys1, this is going to be ball sys. This is going to be ball prob. I'm going to simulate it for 10 seconds, but we need to definitely figure out for the ball model how we can't pick a t-span. We need to run it until the effect terminates the simulation. Okay, cool. Cool beans, man. All right, so let's just try to simulate this. Oh, and you know what? Wait, this is wrong. Ball sys. Okay. Okay, so the initial x and that's true. Okay, so y. So actually, wait. Okay, so now it's time to figure out how to terminate. And I think the only way to do that is you have to use this way. I think you have to use this way. What if you did infinity? I don't know. Does this even work? This is a bad idea. Whatever, let's do it. Oh, okay. That's pretty cool. So we can just do that, and it will stop because of an instability, because it reaches too big of a number. So um um more to dos. So wait, we can delete. Actually, we can delete heater because this is just copied. Whatever. I'm just gonna leave it in. More. Basic ball model need to figure out how to terminate simulation with an event. Okay, so that's actually pretty good progress, I would say. Um, this is fun, dude. I love this stuff, man. This is cool. Okay, so wait, but we need to figure out. So wait, we need a continuous event. We need a continuous event for when um y is equal to 0. We're just gonna do this thing again, just to force the step. So we want to plot. So this is y. So this is what we want to plot. We want to plot sol from like 1 to 7 or something like that. Oh, this is terrible. Let's plot this for like 10 seconds. I don't think that doesn't look right, man. Okay, wait, hold on. No, you know what though? Wait, hold on. Wait, is this still the plot? So wait, hold on. The x position keeps going up. Right, the x position keeps going up. See, why does this look so bad though? Where do I set up the, how do I set up the, I want to, I need it. How do I set the, time step set? Julia Diffie. Whereas, like, there should just be a big ass settings page. Common solver options. There we go. Save at t stops. Save every step. Step size control. Adaptive Absol. DT max. Let's just try to do this. So first off, let's simulate to like 1, or yeah, let's simulate to like, I don't know, 2 seconds. And then this is an argument to solve itself. So then this is going to be like dt max is equal to like 0.01. Wait, so let's redo this. And then y becomes like really big in the negative direction. So x should grow constant. So x should be just a line. That makes sense. But then we should get a parabola here, right? Okay, so then we should do this. Okay, great. So it seems that like a little bit like t equal to 1 is when it does it. Okay, good. And we can do that little hack that I have here, find where sol.t, where sol of, all right, so then this is the time when the ball hits the ground. Yeah. So this is going to be sol where sol.y is equal. Oh, wait, this is the wrong one. This is going to be, oops. This is going to be sol golf. And this is going to be golf ball sys. Okay. So it should be 2 points, right? It should be 0 and, okay, good. So then we're going to take the end point of this, and then we're going to sol golf the whole thing. Oops, that doesn't work. Oh, no, because you know why? Because you have to give it you have to do that. Wait, really? Oh, no, there you go. Yeah, that worked. Okay, and so then the first element of this is the x final is equal to the ball traveled x final meters. 5.3. Okay, so we need to double check all of this for sure, but this is the core of the model. We're now just going to keep improving it by changing things. Okay, all right, that is it for today's stream. Peace out, Larry.